Hello, welcome back to episode 3 of the Microsoft Azure Data Fundamentals. So now we're going to explore databases. What is a database? A database is used to define a central system in which data can be stored and queried in a simplistic sense. The file system on which files are stored is a kind of database. But when we use the term in a professional data context, we usually mean a dedicated system for managing data records rather than files. So basically, we're not dealing with files, we're dealing with pure data. A system that's built for managing data, not files, not blobs, pure data. Now, relational databases. Relational databases are commonly used to store and query structured data. The data is stored in tablets that represent entities such as customers, products, or sales orders. So, the relational databases, we use them to store and query structured data. The data is stored in tables. We use tables to store data to represent entities, whether customers, products, or sales orders. Each instance of an entity is assigned a primary key that uniquely identifies it. As I mentioned previously, there is a there is an primary key. Here it's the ID, order number, that are used to reference the entity instance in other tables. We use it in other tables to reference something specific. For example, a customer's primary key can be referenced in a sales order record to indicate which customer placed the order. For example, this order, the order date, order number, we have the customer, we have the ID. So this customer ID is referring to this customer, Tain at contoso.com. For example, here, product ID, line item, product ID, it's referencing hammer, and so on and so forth. This use of keys to reference data entities enables a relational database to be normalized, which in part means the elimination of duplicate data values so that, for example, the details of an individual customers are stored only once. So basically the relational databases are built so that no duplicates exist. No piece of information is mentioned twice in all of the relational databases. Not for each sales order the customer places. The tables are managed and querying using structured query language, SQL, which is based on an ANSI standard, so it's similar across multiple database systems. So structured query language, that's what's used to reference data and build the databases. Non-relational databases. Non-relational databases are data management systems that don't apply a relational schema to the data. Non-relational databases are often referred to as no SQL database, even though some support a variant of the SQL language. Now, when we say no SQL, we say no structured query language. It's specifically several, it's different database, it's different than the normal SQL. There are 4 common types of non-relational database commonly in use. Key value databases, in which each record consists of a unique key and an associated value which can be in any format. For example, this product has the key 1, 2, 3 and the value, whatever the value is. We see here that the values don't have to be similar in the structure or in the name or anything. Yes, here it's similar, but it's a value which is assigned to a key. No matter what the value is, it doesn't really matter. Document databases, which are a specific form of key value database in which the value is a JSON document, which the system is optimized to parse and query. Here, we'll know customer, which has the key 1 and the document. So basically, whatever the document contains, it just sends back to the key. So basically, it's the key which references some data, no matter how large the data is, it just all gets it gets called whenever we call the key. Column family databases, which store tabular data comprising rows and columns. But you can divide the columns into groups known as column families. Each column family holds a set of columns that are logically related together. For example, here we see key. It doesn't have a family under it, so 1000 to 1001. But customer, it's a column family which contains the name and the address, and the product which contains the name and the price. So basically, what we see here is that under each column there is another column, but it's all of this is called the column family. And these column families are logically related to each other. Graph databases, which store entities as nodes with links to define relationships between them. So basically, I have a node called Ben. Ben reports to Sue and works in the hardware section. Ben is the node and not data. It's not structured properly as if it's in a database. It's a it's a node that contains some data where that defines the relationship between other nodes. It's basically a collection of nodes that has relationships between each other. Okay. Now, exploring transactional data processing. A transactional data processing system is what most people consider the primary function of business computing. A transactional system records transactions that encapsulate specific events that the organization wants to track. Basically, we have transactions. Now, uh, it's how the data is called. Let's learn more about it, and we'll know how it's used later. A transactional data processing system is what most people consider the primary function of business computing. So the primary function of business computing is transactional data processing system. A transactional system records transactions that encapsulate specific events that the organization wants to track. So basically, that the system records transaction that encapsulates specific events. A transaction could be financial, such as the movement of money between accounts in a banking system, or it might be part of a retail system tracking payments for goods and services for customers. Think of a transaction as a small discrete unit of work. Transactional systems are often high value, sometimes handling many millions of transactions in a single day. The data being processed has to be accessible very quickly. The work performed by transactional system is often referred to as online transactional processing, OLTP, are often high volume, sometimes handling many millions of transactions in a single day, such as banking systems. The data being processed has to be accessible very quickly, so the work performed by transactional systems is often referred to as online transactional processing system. OLTP solutions rely on database systems in which data storage is optimized for both read and write operations in order to support transactional workloads in which data records are created, retrieved, updated, and deleted, often referred to as CRUD operations. Basically, when we're dealing with databases, the databases are built for higher, faster read and faster write. And uh, in order to support now transactional workloads, the workloads are separated into uh, four main, uh, four main types of transactions: create, retrieve, update, and delete. CRUD. These operations are applied transactionally in a way that ensures the integrity of the data stored in that database. To accomplish this, OLTP systems enforce transactions that support so-called ACID semantics. We'll know what ACID means in a second. Now, these operations are applied transactionally. So, I send a transaction. The transaction says create a customer in a way that, or delete a customer, update customer information, give me the customer information in a way that ensures the integrity of of the data stored in the database. Now, when a certain customer is retrieved, we're holding the same information, nothing is affected. Well, we're getting back the same type of information immediately, nothing is tampered with, and it's all and it's all in the integrity of the data is maintained. Now, uh, OLTP systems enforce transactions that support. Now, there is ACID semantics. Let's read more about them. ACID stands for atomicity, consistency, isolation, and durability. Atomicity. Each transaction is treated as a single unit, which succeeds completely or fails completely. For example, a transaction that involved debiting funds from one account and crediting the same amount to another account must complete both actions. If either action can't be completed, then the other action must fail. So basically, it's all containerized. It's like I'm sending five messages. If one of them fails, fail all the requests that I sent. All the five messages fail them immediately. If all of them succeed, then the transaction is then the all then the transaction requested is done properly. Consistency. Transactions can only take the data in the database from one valid state to another. To continue the debit and credit example above, the completed state of the transaction must reflect the transfer of funds from one account to the other. Now, for the consistency, at the end of the transaction, we'll make sure that, for example, as the example mentioned here, we wouldn't have negative valid state to another. Some of the valid states would be that the account wouldn't go into the negatives. That's one of the valid states. Uh, the account doesn't exceed a certain number. That's another valid state. So when the transaction is finished, we make sure that the funds were actually transferred, even though it might be only be simple numbers, but it just reflects properly. And we make sure that valid states were maintained. Consistency. Isolation. Isolation. Concurrent transaction cannot interfere with one another and must result in a consistent database state. For example, while the transaction to transfer funds from one account to another is in process, another transaction that checks the balance of this account must return consistent results. The balance checking transaction can't retrieve a value for one account that reflects the balance before the transfer and the value for the other account that reflects the balance after the transfer. Now, isolation. Now, each transaction must be done properly. If we're talking the transaction that retrieves the data for two accounts that are trying to transfer money for each other, we need both to be before or both to be after the transaction is finished. It can't be in the middle of the transaction, one of them is before and the other is after. We need to treat each transaction as a full as a unit, even if it was multiple transaction, multiple deductions, multiple additions to certain accounts. So we need to isolate each transaction on its own. We don't want any interference to happen. Maybe perhaps two transactions were made to deduct from one account. One of them, that for example, the account was on $7. One of them was -5 and the other was -3. The first transaction remove the $5 from this account to another account, it would succeed, but the next one would fail. Not both of them would fail because they are isolated. They are two different transactions. They might fail completely as a unit, or the other one might succeed and the other might fail because of the consistency and the valid states and the isolation because each transaction is isolated. Durability. When a transaction has been committed, it will remain committed. After the account transfer transaction has completed, the revised account balances are persisted so that even if the database were to be switched off, the committed transaction would be reflected when it is switched on again. So, for example, I removed $5 from the account number 1 to the account number 2. If I switch off my system, it's not supposed to revert. It's supposed to, whenever I shut down my system and turn it back on, it retains its last updated data. It updates regularly. It automatically saves its own data. OLTP systems are typically used to support live applications that process business data, often referred to as line of business (LOB) applications. Now, OLTP systems, again, OLTP systems is online transactional processing, are used to support live application. For example, business data, banking systems. Banking systems need OLTP, online transactional processing, to process its data, to process the transfer of its funds and everything else. I will stop episode 3 here and I'll continue in the next episode.